Hello, everyone. Today we are going to be graphing rational functions. Before we do so, we're going to take a couple or just a minute or two just to review a couple key and important steps. So if you guys could please at the top of the page, I would love it if you would try the two ignite problems at the top of these notes. So pause your video and give these two a shot. All right, so let's look at the first one. So answer is up. For this one, because if you look at the main problem, we have one fraction and I'm subtracting another fraction. This is something where if ever you're adding and subtracting fractions, we have to get a common denominator. So first step was we had to factor each of these denominators because you need them factored in order to choose what's going to go in your common denominator. So since this first fraction's denominator factored into x plus 2 times x plus 2, then obviously both of those had to show up in my common denominator. The second fraction, x squared minus 4, that factored into x plus 2 times x minus 2. Now you only have to put what it's missing. So it already had an x plus 2, but it didn't have the x minus 2, which is what we had to add. Now, once you choose your final common denominator, then it's really just a matter of multiplying each term by what it's missing. This first fraction obviously had both of the x plus 2's. Since it was missing the x minus 2, that is what we multiply by. Same concept with my second fraction. This one had, now this one wasn't quite the same. This one had the x plus 2 and the x minus 2. It was missing the x plus 2. So that's what we had to multiply by. Now, once you get your common denominator, then it's just a matter really of simplifying your numerators. I multiplied out the x plus 2 times x minus 2, and then obviously distributed that negative 6 to the x plus 2. Combined like terms, multiplied everything out, and you are left with your final answer of x squared minus 7x minus 14 over your common denominator. Now, that's not as applicable to what we were doing today. Question 2, though, is really going to kind of get us in that mindset. And because when we talk about what is the vertex of f of x equals x minus 3 squared plus 7, this is just simply a quadratic in vertex form. And if you'll remember vertex form, that's a times x minus h squared plus k, where the vertex is always at h comma k. Now, you're probably saying, well, Ms. Hardy, why are we talking about the vertex of a quadratic? We're not working with quadratics. It's still kind of the same concept. It's whatever's in with your x. H is always kind of weird. It's always we take the opposite sign of it. So in this problem, since it's a negative 3 in my problem, that means a positive 3 is going to be what goes in the x spot. And k is always the number that's your y coordinate of the vertex. And that's always that's always the number that's not with x, in which case it's positive 7, and that one doesn't change signs. Now, the great thing is even if we're not working with quadratics, if we're going to find that vertex, although I will let you guys know, it's not really called a vertex when we're working with rational functions, but it is an important point that we're going to go ahead and find. Now, the vocab terms I'm going to come back to. The first thing we're going to start off with, what is the standard form of a rational function? And it works a little bit kind of in the same way. We're going to start by talking about what is our standard form. Well, we have to start with a rational function. And x is always going to be on the bottom, obviously, with your h. It's going to be x minus h on the denominator. And then k is going to be kind of a number that's not in with your fraction. Now, like I said, that h comma k is a very important point. This isn't called the vertex, though. This is just the point where, forgot the asymptotes cross. Now, you guys are probably thinking, well, Ms. Hardy, what is an asymptote? Well, if you look up in the vocabulary section, an asymptote is simply a straight line approached by a curve that goes to infinity. And it is invisible. Now, you're probably starting to think, well, what? There's invisible things on graphs? Yeah, definitely. Once we start working with functions, we're going to, and especially this is true second semester, but we're going to graph some functions that have some kind of weird things going on in them. And with rational functions, you start to experience your first asymptotes. And that's because asymptotes are kind of created when you have variables on the denominator of fractions. Because technically, fractions are just division. So there are certain numbers out there that you are not allowed to divide by. So this makes more sense. Let's look at an actual example. So if you guys look all the way down at the bottom of your page, the last example right under that standard form of rational functions, we're going to graph our first example, which is example number 1. And it's f of x equals 3 divided by x. Now, first things first, it might help to kind of think about this in standard form. Now, you won't always see it written initially in standard form, but that number on top, it's technically there's no number with x, and there's also no number on the end. But all that really tells me is that if I'm working with my h comma k, it just means my h is going to be the number opposite of what's with my x, which is, can't really take opposite of 0. And my k is always going to be the number that's on the end. So this 0, 0, these are going to create kind of those first asymptotes. Now, I accidentally put these a little bit out of order, but if you guys look up at the top where it says asymptote, it says vertical asymptotes, these are x equals number. And horizontal asymptotes, these are going to be your y equals number. And these are no different than any lines. If I said graph a vertical line, those always start as x equals. It's just that when we graph asymptotes, these we're going to use dotted lines for, because technically they're invisible, but they do act as kind of like fences. And typically, just so you guys know, asymptotes, technically these are lines that you really can't cross. There are exceptions to this, and you'll explore those a little bit more if you go kind of further into the math field. But for the most part, asymptotes are lines that curves can't cross. So they kind of go hand in hand with your vertical asymptote. This always corresponds with your x value. So since x is 0, that tells me that your first vertical asymptote is going to be at x equals 0. Now, if you graph this equation on your calculator, it's not going to show up, but this is something when I ask you to graph these functions, this is something I am going to be looking for. I do need to see a dotted line going, a vertical dotted line going through x equals 0. And same with my horizontal asymptote. This is created by whatever the y value is. So y equals 0, that is our horizontal asymptote, and it's going to go horizontally through y equals 0. Which in this case, really, these are just your axes. Usually those are other numbers, and we'll see what that looks like in just a moment. But because rational functions have these asymptotes, what happens is it does some kind of weird things to your domain and range. Now, if you guys look up under vocabulary, it might make a little sense to kind of remind ourselves of what domain and range are. So domain, this is really what you plug into the function. And obviously, these are really what we always know as the x values. So these are the things you're allowed to plug in. And the range is obviously kind of like the list of numbers you get out when you plug in those x values. Now, because in this case, if you start looking at your asymptotes, my domain always kind of corresponds to that x value. So, AKA, we have to keep in mind what that vertical asymptote is at. Because for the domain, technically, since we have a vertical asymptote is at x equals 0, what that tells me is that we're not allowed to plug in 0. Now, I want you to think about why. If you look up at our function and I plug in 0 in for x, are you allowed to do 3 divided by 0? No, actually. And that's where asymptotes start to come from. They're numbers that you're not actually allowed to plug in. So for my domain, technically the domain is all numbers. It's just, it can't be equal to 0. Now there is a more formal way that we notate this. Technically, you could put just x cannot be equal to 0 as your domain, but sometimes you'll see some different notation. And this is one of those notations. Usually, kind of like there's one notation where we'll put these fancy brackets around it. And this is just kind of like a wall right here. And on one side of the wall, what we do is we put kind of like what realm of numbers we're working in. And this starts to matter because obviously certain realms of numbers, kind of you're not allowed to plug in certain numbers. Now for us, our domain, it's always x. And we're always dealing as part of the real, working in the real numbers, which is basically just we're allowed to have all negatives, all decimals, 0, anything that I can plot on a graph. So how the word in is represented by a symbol. It's kind of like a C, and it has, ooh, that's not one. It is a C, and then it has a line through it. So this just in math, just so you guys know, this just means in. And you could either just put an R here, or you put the fancy R, which is kind of like two kind of like bars next to each other. So it's an R, like a thick kind of stem, if you think about it. And that just means whatever number you pick, it's a real number. And then we'll put right after, we'll put the x cannot be equal to 0. So whichever way you like writing it, I'll accept both. But you do need to know this, especially because the SAT will use this notation. So range is very similar. We say y is backwards c in the real numbers wall. And here my horizontal asymptote is y equals 0. So that is something that you're not allowed to get out. You'll never get y equals 0 out, no matter what x value you plug in. Now, when it comes to the actual graphing, this isn't fancy. This is more just, if I know my asymptotes are going to be at 0, 0, let's just pick 3 on one side and 3 on the other side of 0. So 0, let's do -1, -2, -3. And let's do 1, 2, and 3. Let's stay pretty simple. If you guys go into your graphing calculator, and obviously I'm going to type in 3 divided by x. If I go and click graph, we can see kind of what this graph looks like. And this is what all of your rational functions are going to look like. Now, maybe not necessarily obviously exactly like this, but your shapes, because of those asymptotes, it causes some weird things to happen. So obviously you're going to see that these blue lines, they look like they're going to cross your axes at some point. But remember, we have asymptotes there. If I look and start to see what's happening to each of those values, you're going to see that I actually am never going to cross them. So if you go to your table, if I go second graph, this is where you can get all of those other values. So I can see 1, 3 is a point on this graph. Makes sense that at 0, there's an error because that's where my vertical asymptote is. I'm not supposed to get a point out for that. That's why this is taken out of the domain, because you don't actually get an answer out. So I'm not going to click back and forth, but if you fill in your table, it's going to be -1, 3. It's going to be -2, -1.5, and -3, -1. And then 1, 3, 2, 1.5, and 3, 1. Those 6 points are going to be the points that I'm going to look for. So if we go over on our graph, I'm going to graph those right now. Now, once we graph these points, now it's a matter of filling in those curves. And this is where I'm going to be a little bit of a stickler, because obviously we want to go through all those points, but we're still going to carry that curve kind of as close as possible to that line. We still have the arrows because technically it goes on forever. It just gets kind of really small and really large really fast. So if you please make sure you're not just crossing, because some of us tend to get a little careless with our graphs. You have to make sure, remember, we're not crossing the red or green line. You are not allowed to cross those asymptotes. So when we kind of fill in our graphs, we want to try and be a little bit neater and a little bit more careful with those graphs. And there is the function f of x equals 3 over x. So when it comes to those different functions, now just so you guys know also, when it comes to standard form, sometimes in standard form, this is also kind of considered a. So that a value sometimes obviously can be of another number. It doesn't have to be 1, but no matter what, though, that is kind of the ins and outs of graphing a rational function. So what I want you guys to do is I want you guys to pause your video and I want you guys to try the 2 problems on the next page. So pause your video and give those 2 a shot. Now, answers are filled in for both of these. Now, if you look at obviously the different functions here, for number 2, this one we had different numbers. Our kind of center point where our asymptotes are going to cross, we take the opposite of what's with our x, and obviously whatever is going to be outside, and those become your x and your y. And those obviously create your vertical and your horizontal asymptotes. And then the domain and range kind of follow suit. So obviously your graph can look a little bit different. Is going to look a little something like this. But obviously if you guys do have any questions, I will have some time in class for if you want to ask any questions about these 2 examples. But if you want to try a couple more on your own, Miss Hardy is also going to go over these 2 as well. So in class together. But if you're feeling good and you're done with all of these problems, then if you want to get your homework out and start working on that, then that is something that you can do now. So good luck, guys. As always, email Miss Hardy or ask Miss Hardy in class if you have any questions. Thanks, guys.